Okay, so now that we discussed in the previous lectures these stability margins, so what if the stability margin of our system is not satisfactory? And this is where we need to change that. So and this is where the control design in the frequency domain becomes quite interesting, because the controller is essentially cascaded with the actual system. Okay, so and this means that the open loop transfer function is directly affected by the controller, which is in cascade with the system. So if we can modify or design the controller, our controller, such that we can modify the gain margin or the phase margin, that would be great. And this is one of the main objectives of designing control system in the frequency domain. Okay, so we have the controller is modifying the open loop characteristics, and is thus it can directly affect the gain margin and the phase margin of our system. Okay, so today we will be talking about two new controller structures or controller architectures. We discussed in our previous lectures, we discussed the PID controller, which was one of the controller structures we talked about. Today we will talk about two new structures called phase lead and phase lag compensators. Okay, so the transfer function of both compensators is essentially the same. The difference will become clear right now. Okay, so we have a gain and we have 0 and a pole, just a real 0 and a real pole. It's quite simple. So this is the main structure of the controller or of the lead or lag compensators. The only difference between them is basically the location of the 0 and the pole. So if the magnitude of the 0 is smaller than the magnitude of the pole, then this is called a phase lead compensator. Okay, so this compensator is a phase lead compensator, and if we reverse that, if we make the pole smaller than the 0, then it becomes a phase lag compensator. Okay, so we will start our discussion with the phase lead compensator. So basically the 0, our 0 is smaller than the pole. The value of z is less than the value, smaller than the value of p. So how can we design this controller to meet certain stability margins? Okay, so in order to answer this question, we need first to understand what does this controller look like in the frequency domain. Okay, so what is the transfer function of this controller in the frequency domain? And if we were able to get that, so we can then know how it can affect the overall open loop response in the frequency domain, and then we can calculate the new gain and phase margins after we add the compensator. Okay, and this is one of the advantages actually of using the log domain, as we become clear, because when we cascade the controller with the actual system, so we are multiplying them in the and this multiplication becomes addition when we take the logarithm, and it makes things quite simple. Okay, so let's just start this step by step. Okay, so if you want to obtain the transfer function of this controller in the frequency domain, what will we do? All we need to do is just replace s with j omega, and that's it. So if we just replace every s by j omega, we obtain the frequency response of our controller. Okay. Okay, we discussed this already many times before. So we talked about that the Laplace transform is essentially, we can observe it as a three-dimensional plot. The magnitude response of the Laplace transform is a three-dimensional plot, and the intersection with the j omega axis, this one here, the intersection with the j omega axis is actually the frequency response. So we obtain the frequency response. So since s is actually sigma plus j omega, so all we do is that we put this sigma, we set the sigma to 0, and we remain with s equals j omega. Okay, Okay, so we will modify this expression a little bit. Okay, I'm gonna write it in this form. Okay, so we will have a new gain k bar, and the numerator becomes 1 plus j omega over z, and the denominator becomes 1 plus j omega over p, where k bar is just basically k times z over p. Okay, so it's just simple mathematical transformation. So we didn't do anything really serious here. But yeah, it will become clear now why we did this step. Okay, so now we can observe that this controller, our controller transfer function, is the multiplication of three terms. So we have this gain term multiplied by this this term, which is coming from the 0, and then it's multiplied by 1 over the other third term, which is coming from the pole. Okay, so then when we take the log, as we do in the so when we take the Bode plot, so the Bode plot is just the log of that. So we take 20 log to the base 10 of the GC of omega. So this multiplication is transferred into, or changed into, an addition. So if we are able to obtain the Bode plot of this term and this term and this term, then all we do is just we add them together, and we get the overall Bode plot of frequency response of GC of omega, which is at the end multiplied by G of omega, because we know that the GC and the G are multiplied together. So we have the GC followed by G. So then if we have the Bode plot of the G, the Bode plot of the GC, we just add them together and we get the overall frequency response, or Bode plot of the system with the controller. And from that we can extract the new gain margin and phase margin, or the other way around, and we can try to design the controller such that we achieve a certain gain margin and phase margin. Okay, and by the controller design we mean that we need to obtain the controller parameters. What are the controller parameters in this case? We have the gain, we have the location of 0, and the location of the pole. So these are the parameters that we need to tune in order to satisfy certain requirements or specifications. So this is very similar to any control design problem. Like we talked in the PID controller, we had the proportional, integral, and derivative gains. So we tune those gains in order to achieve certain characteristics. Same thing here. We have the location of the 0, location of the pole, and the gain, and we tune this in order to obtain a certain gain margin and phase margin, or certain stability margins. Okay. All right. So let's bring this a little bit further. So when we take the log, okay, so we said that we have those three terms, so 20 log k bar plus 20 log the magnitude of this term plus 20 log the magnitude of this other term. So the Bode plot is essentially actually 20 log of the magnitude, because this is the magnitude part, and the other part is the phase of G of omega. Okay, so we are left with, so when we expand this term, we have three separate terms. So we have 20 log, okay, so this is to the base 10. I'm just going to write it every time, so that we will assume that this is the base 10. Okay, and plus another 20 log, okay, magnitude of 1 plus j omega over z, and the minus 20 log magnitude of 1 plus j omega over p. Okay, so as we said, it's just simply, it becomes an addition and a subtraction, so it becomes quite easy to do. And the same thing for the phase. So the phase of GC of omega is basically the phase of the first term, which is 0, okay, plus the phase of the numerator part, and the minus also the phase of the term which is coming from the pole. Okay, so these are the expressions we have. Okay,